Okay, so 9.4 comparison of series. We have direct comparison test, and pretty much what that is comparing two different series in order to determine if the series is going to diverge or converge based on what's called a benchmark series. And for that, we're gonna have you're gonna have some things you're gonna have to assume. And so starting off, you're gonna have to assume that your a sub n value is greater than or equal to 0, and that your b sub n value is also greater than or equal to 0. And so having said that, we're going to have two different properties or rules. And our first one is going to be the convergence one, which is saying that if your b sub n series converges and the a sub n is less than the b sub n, then the a sub n is also going to converge. And for the second one, we're going to have if a sub n diverges and a sub n is less than b sub n, then our b sub n is also going to diverge. Okay, and so for number one, pretty much what it's saying, the convergence series, it's saying that if you've got a series that's smaller than a convergent benchmark series, and for number one, our benchmark series is going to be this b sub n, then your series must also converge. So here in this case, since a sub n was smaller than b sub n, then a sub n must by rule also converge. Now for number two, this is a little different. This is going to be the divergence one, and so pretty much what this one is saying is that if your series is larger than a divergent benchmark, and so here our divergent benchmark is going to be a sub n, and so here if it's larger, then your series must also diverge. So here our b sub n is greater than our a sub n, so that must also diverge. Okay, and so for this to make sense, we're going to do a couple of practice problems. Okay, so for the first one, we have the series of 1 to infinity. It's going to be 1 over n cubed plus 1. And so with this, we're going to use the direct comparison test in order to tell if it's going to converge or diverge. And so we can start off looking at the function and evaluating what series it looks like. And for this one, it's going to resemble a p-series. And what that means is that the function form pretty much looks like 1 over n to the p. Because right here you could see 1 over n to the 3 and p is going to equal 3. And so knowing that it resembles a p-series, we can tell that with our p-series rule we have if our p value is going to be greater than 1, then it's going to converge. And if our p value is less than 1, it's going to diverge. Alright. And so when we're given that, we're going to rewrite our series in the more simpler form, forgetting about the 1. And so with that, we have infinity n equals 1. We're going to rewrite it as 1 over n cubed. And given this simpler form, we can go ahead and look at our rules for p-series, and we can see that our p-value is greater than 1 because here it's going to be 3, and so that means our series right here is going to converge. And so given that, if we know that this series is going to converge, then that means for a that this function right here is also going to be converging.
Hey guys, so moving on to the second example. It's kind of similar to the first one, however, we're going to be using a slightly different approach. So instead of the p-series that Ryan used, we're going to be using the geometric sequence or series. So the formula is going to be a n equals a1 times r to the n minus 1. So if looking towards our problem, we can actually take out the plus 2 because it's negligible in the kind of problem that we're looking at. So if you rewrite the problem, just bear with me as doing this. Right, you can simply write it as 1 over 3 to the n. Now you can furthermore rewrite this by just having it simply 1 over 3 to the n. Now, and you can see how that coincides directly with the formula that we have in this portion right here. So let's look at the rules that we have for the geometric series. If the absolute value of r is less than 1, then it will converge. Inversely, if the absolute value of r is greater than 1, then it's going to diverge. So if we take those rules, and look back to our original problem, seeing how the absolute value of 1/3 is less than 1, then the answer to this problem is that it's going to converge.
Okay, so for our last example, at first glance it doesn't really look like the other ones we've been doing, but if we go ahead and evaluate it, we can see that it's going to ultimately come back and look like a p-series again. So we have 1 over root n minus 1 in the original equation. So if we want to go ahead and simplify that down, again, forgetting about the minus 1 because we really don't need it, we can bring it back to 1 over root n, and if we want to go ahead and simplify that, it's going to come to be 1 over n to the 1/2, just power over root. And with that, we know we can relate it back to our p-series like we did for the first one. Just to remind you guys, our p-series general equation is going to be 1 over n to the p. And again, when p is greater than 1, it's going to be convergent. And when p is less than 1, it's going to diverge, right? So with that, if we look at our problem, we're left with 1 over n to the 1/2. And so with that, we're going to look at the p-value, and here, if you look, our p-value is going to be, this time it's less than 1 actually. This time p equals 1/2. And so given that, we know that this this form of the series, 1 over root n, is actually going to diverge. And since we know that, using our direct comparison test, we can go back to our initial problem, which is 1 over root n minus 1, and also conclude that it's going to do the same thing, and it's going to diverge.